Hello everyone, welcome back to lesson number 9 for BC Calculus. This is where we're looking a lot into derivative graphs and we're comparing those to f of x, and today we're going to talk about how we compare f of x graphs or derivative graphs to f double prime of x graphs. So we started out the first video with a little visual picture, and so we're going to talk about that one here. So it says let f be twice differentiable on the open interval. So let me actually draw a f of x graph. So this will be an f prime of x graph. And it's going to look very similar to the one that I did in the first video. So now this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5. So let's actually take a really quick summary of what we did, or a reflection of what we did in the first video. If I want to talk about where f of, and we'll get to concavity in a second, so if I want to figure out where f of x is increasing, right, on this graph, then it's going to be increasing from 0 to 1. So this is a quick little review of what is, and then 3 to 5. All right, so this is where f of x is increasing, and we talked about that because f prime of x is greater than 0. So we're looking at the y values, right? So where is f prime of x decreasing? So f prime of x is decreasing, and that's going to be on the interval from 1 to 3. And that's where f prime of x is less than 0. And then the other thing we talked about is where is f of x have a maximum. And we talked about there are 3 places that this could happen, right? So it's, again, where a maximum, well, we got to look at where f of x changes signs, right? And we need to be more specific on that. It's changing signs from plus to minus, right? Changing sign from plus to minus. So here I'm increasing and then I'm decreasing. So I'm going to do at x equals 1, and then I'm also going to x equals 5. And then finally, from last video, where's f of x got a minimum, and that's going to be at x equals 3, because f prime of x changes signs from negative to positive. And again, I'm going to do a summary at the very end of our lesson set here and talk about that. So that's where we go. So this is negative to positive. So what I just did in these multicolors is what we should have learned from the first video. Hopefully that's what you should have gotten out of it. Those four things is really what it is. So now let's talk about concavity. So I'm going to get rid of all this stuff. I'll draw my picture, my little graph again, and we'll talk about now concavity. Okay, so I went ahead and got our graph back to where it was. And so for f of x, so everything that we talked about here was f of x. We looked at y values, right? We looked at the y values of f prime of x. We looked at the y values. Where is it positive? Well, that's where f of x is increasing. Where is it negative? That's where it's decreasing. Where is it changing signs? The y value is changing the signs. Positive, negative, max, negative to positive, minimum. Now if we're looking at the second derivative, we're not looking at signs here. We're going to take f of prime of x, and we're going to start looking at slope. Okay? So if it's asking us where f prime is increasing, well, again, ladies and gentlemen, it's increasing. This is f prime, right? It's increasing from 2 to 4. So just like we talked about in the first video, now f prime of x is increasing here, which means that my second derivative is greater than 0, which then in turn says that my function f of x is now concave up. So from 2 to 4, the graph for f of x is going to look concave up. Up for like the U, right? Up for U, concave up. When I'm looking at decreasing, so when is f of x decreasing? Well, that's from here to here, and then from here to here. Well, then that means that the slope of my slope, right? So the second derivative is the slope of my first derivative. That is less than 0, and that means that f is concave down. And like I said, we're going to do a nice little summary at the very end of this lesson set. All right? So now I can see this. So now let's go talk about the question. And by the way, down, I always say that down looks like a sad face. and up looks like a happy face, and it also is the beginning of the U for up. So that's what we're going to do here. So let's actually answer the question that's asked, and then we will go look at a first derivative graph and talk about concavity. So what does this mean? So if you look at the question, it says, how does the second derivative help us find points of inflection? Now this points of inflection they're referring to is points of inflection for f of x. So what is a point of inflection? Well, a point of inflection is where we change from concave up to concave down and concave down to concave up. So this is where we have a change in concavity. And so you guys can see in my little multicolored thing right here that, again, we're going concave down here, and then we go concave up here. So at x equals 2, we have a point of inflection. We're concave up here, and we're concave down at x equals 4. So what can you say visually about this graph of the first derivative that tells you where we have concave up and concave down? So we have point of inflections where f prime of x has maxes and mins. Okay? And again, not to be confused with f of x having max and mins. We've already talked about where f of x have max and mins. But this is where now when the derivative has a max or min, then that's where we're going to have our point of inflection. Okay? Because our slope of f prime of x actually changes signs. So that's our little overview for that particular question. So now let's go and look at a first derivative graph that's much nicer than this one and talk a little bit more about what we just did. Okay, so we have another example of our function, and it looks very similar to, so I actually still have the workup from the first video that I did. This is talking about where we can find max and mins of f of x based on the first graph, our first derivative graph, and now we're going to look at concavity of the first derivative graph. So it's first of all going to say, let's identify all the horizontal tangents. So all the horizontal tangents in this graph. So we have a horizontal tangent at x equals c. We have a horizontal tangent at x equals e, and a horizontal tangent at x equals g. So I have horizontal tangents at x equals c, at x equals e, and x equals g. Okay? So it says, let's make a sign chart using slope. So what I always like to do here is when I do a sign chart, I always identify what I'm actually looking at. So when you guys see throughout this course, I like to say that I'm plugging into the derivative, or I'm plugging into the original, or I'm plugging into the second derivative. So that's the idea of this. I did this when we talked about particle motion, right? We did this example where I said v of t is here, and then acceleration is here. And so that's what I like to do. I like to always write out, when you guys are looking at the chart, what am I plugging into? So we know that here, there's 0 here, here, and here, right? For slope, we're looking at slope of this. So this is going to be the slope of f prime of x. Okay, slope of f prime of x, I'm not a big fan of that, so let's actually write that better, because we never want to justify by actually saying slope of. So what does that translate to? That translates to, oh, now we're looking at the second derivative. So we're using the first derivative graph, but we're finding the slope of the slope, which is their second derivative. So from A to C, our slope is positive. I don't care about above or below the x-axis. All I care about now is that it's positive. And then from C down to E, it is negative. From E up to G, it is positive. And then G to I, it is negative. So what can we say about this? Well, where is it concave up? Well, it's concave up. And again, I'm going to start abbreviating this CU. It's concave up on the interval from A to C. And it's concave up from E to G. And you know why? For two reasons, actually. There's two ways you can justify this. You can say that the second derivative is greater than 0, which is great. Or you could say that the first derivative is increasing. Either of these justifies the same thing. When f of x is increasing, your f of x is concave up. Or where is my second derivative positive, which is the slope again of f prime of x. So either of these are fine. You do not have to write both of them. So where is it concave down? It didn't ask that in this example, but where is it concave down? It's concave down from C to E, and then G to I, right? G to I. And then it says determine the x-coordinates of any points of inflection. Well, we actually already know these points of inflection. I got a point of inflection at x equals C, because remember, we're concave up from A to C, and then we go concave down from C to E. So we change concavity. We go from a plus to a minus. Here, we're concave down to up, so at x equals E, we also have a point of inflection, and then at G, we also have a point of inflection. And there should be no surprise that what you see here matches exactly what you see here. Now, we do not say to justify, we do not justify that, that the point of inflections are the horizontal tangents. Okay, we don't say that. What we say is that f double prime of x changes signs. Okay, changes signs. We have to change the signs. All right, so that's going to be how you're going to justify points of inflection. And it's not going to really matter. I mean, if it asks you, point of inflection, yeah, this is concave up to concave down, it's positive, negative, but all you need to justify is f prime of x changes signs. So let us do our next example and see what you guys can do with this. Okay, so to finish up this video, I have taken the graph from the very beginning of the packet and drawn it over here. And so these are the 7 things that we need to know how to do based on this. So I've also changed the fact that this is a derivative graph now. So where f of x is increasing, decreasing, max, and min. So I put them all above here because for all of these functions, you're going to look at the y values. Okay? So where f of x is increasing, we're going to find out where this is positive. So we're going to go ahead and just, I guess, say this is negative infinity. I don't know why, but just negative infinity to a. And then we're going to look at, again, where, again, this is positive. So now C all the way to G. And that's it. So f of x is increasing right here and all of right here. And that's it. Where is f of x decreasing? Well, it's decreasing from A to C. Okay. And then it's also decreasing at H, if we will, all the way to K. And then from K all the way, and we'll just call this, I don't know what this is, I guess that's the x-axis, so we'll just call this to O, all right? And then it's going to be from K to O. So it's where everything's below the x-axis. Where is our local maximum? Well, there are 3 spots that we care about for this. We care about spot 1, spot 2, spot 3. And technically right here, but it doesn't change signs. It's negative to negative. So for this one, we're at positive and negative. So we have a max at x equals A. And we also have a maximum at G, right? We're positive to negative, also at x equals G. Where's our local minimum? Well, that's going to be at C, right? It's going to be negative to positive, x equals C. So again, looking at the y values when it's above the x-axis, and again, this is where f prime of x is greater than 0. Please do not justify by it's above the x-axis. You justify it by f prime of x is greater than 0. Decreasing, it's less than 0. This is where f prime of x changes signs from positive to negative. This is where f prime of x changes signs from negative to positive. All right. So let me go ahead and erase those. Okay, so now we're talking about where f of x is concave up. Well, now this you look at slope of f prime of x. So where are we starting to be positive? Well, we're positive from B all the way to what looks like F. Let's just say F there. It also looks positive from J to K, and then from M to O. Okay, concave up at those particular values. Where is it concave down? Well, this is where we're looking at slope that's negative. From this point right here, let's just call this smiley face. That's a horrible smiley face. So from smiley face all the way to B, we have negative slope. And then it looks like from F, this is a not so good example to, let's say H, right? It's negative all the way to H. And then it's negative again from H. And so this is actually kind of H to the left and H to the right, if we want to be more specific about this, right? So to the right to J. And then looks like from K to M, right? Hopefully I got them all. Now, point of inflection, I'm looking at this graph and, I'm thinking, well, it's good, but it's not fantastic with what I'm seeing here. And the reason why is technically it's not differentiable here. And it's also not differential here. And I thought that'd be a good chance to say that F double prime here would be undefined for both those places. So the only true, place of concavity that we want to do here is we don't want to go and say B, right? Because that's, again, an example. Because students always ask, can we always look at where the concavity changes? Well, no, it's not differentiable there. So I can't choose B. X equals B is not a solution to this because it's not differentiable. So then we're going to go and look, okay, where else does it change? We'll change it to F. Well, F is actually, it's got a horizontal tangent. So we know that that's going to be 1. So F of X is 1. Well, where else does it change? Well, H, clearly not, right? It's not even continuous here. So it can't be differentiable there. Again, we have a sharp corner with this problem. Looking at K, right? I think that's K. So looking at K here, this one is a horizontal tangent. So X equals K is an answer. And then over here at approximately X equals M. So I like this example because, I want students to know that it's not everywhere you see a change in concavity. You still got to take into account that this value right here is not differentiable. This is also not differentiable, and this is not differentiable for the fact that we have a sharp corner and a cusp and an asymptote, or the fact that it's not continuous. So those are our solutions to this problem. So in video number 3, we're going to analyze derivative graphs quite a bit more, and then I'm going to do a nice little summary for you guys. So I'll see you guys back in the next video.